We are now in lesson 6.3, and you can see our title today is going to be Geometric Sequences and Series. So what is a geometric sequence? And I've given you an example here. A geometric sequence is, you can think of it as a list of numbers, and we call these numbers terms. A list of terms that follow a specific pattern. And to be a geometric sequence, the pattern has to be this. To get from one term to the next, we are multiplying by the same number each time. And you've probably already figured out that every time to get from one term to the next, I am multiplying by 3. 6 times 3 is 18, 18 times 3 is 54, and so on. So that number that we multiply by each time is called the common ratio. And you might be wondering, well, why do we call it a common ratio? Well, it's arrived at by taking the terms in pairs, starting off with the first pair, and you can always determine the common ratio by doing division. 6 divided by 2 is 3. And then I would do the next two. 18 divided by 6 is 3. And if doing this division process with the pairs of numbers each time results in the same quotient, 54 divided by 18 is 3, you get the picture, then I truly do have a geometric sequence. So it's multiplication that is the operation that I use to get from one term to the next. So and you can think of it as division helps me determine, if it's not obvious, division helps me to determine what that number is that is being multiplied. And so you'll see the letter R refer to that number, and it comes from the common ratio definition. Okay, so that's a sequence. So what does it mean to have a geometric series? Well, when we take that sequence, we take the terms and we add them together to come up with a sum. That is a series. So the sequence is the list of terms that follow that pattern of multiplying by the same number. And the series is the sum of those terms. Okay? So with that said, we've identified some terminology. And so let's just make a connection real fast before we dive right into homework examples. Let's just make a connection to where we were and how does that relate to today where we are. Okay, remember this, we talked about in lesson 6.2 the function template, if you will. What does exponential growth or decay look like in equation or function form? And it looks like this, and the only thing that differentiates growth and decay is this letter B. When B is greater than 1, we have growth. If B is between 0 and 1, we have decay. All right? So what I've done here is I've just given an example of an exponential growth function or equation. And so think about this if this were a real-life scenario. And remember, when we graph these real-life scenarios, the x-axis is generally a time factor, whatever, years, months, days, hours, whatever. So we have time, and then we have whatever the item is that's growing, number of whatever this would be talking about. So obviously there's no such thing as negative time, so we start at the time 0, in other words, x being 0, which will give us the initial value. And so it's another way of saying, earlier I said you can always identify the initial value by looking at this number in the A spot. Well, using x as 0, which puts me right here at the very beginning, before any time has passed, I'm going to get that initial value because 2 to the 0 power is 1. 1 times 3 is 3. And so I get an initial value of 3, in this case, if I input 0. All right? And so we would just keep on going maybe. What about if x is 1? So if x is 1, I get 3 times 2, which is 6. That would be considered the second value, but I got it by letting x be 1. To get the third value, I would let x be 2. 2 squared is 4. 4 times 3 is 12. So are you seeing how to get the third value in the, if I'm plotting points in sequence, the third value would be inputting 2. The fourth value, I would input 3. 2 to the third power is 8. 8 times 3 is 24. And so it's 1 less because I started off at 0. At when no time has passed, we need that point, and that's also of course, the y-intercept. Okay, so hopefully that makes sense, how we generated points from an exponential growth function that was given. So how does that compare and connect to what we're going to talk about today? All right, well, geometric sequences, we already talked about how they are lists. It's a list of numbers that follow a specific pattern, multiplying by the same number every time. They are the discrete form. Okay, remember that word discrete from way back in chapter 1, I guess. Discrete means that it's basically not a continuous graph. Well, exponential growth or decay, we've already talked about, is continuous. When we sketch this growth graph, whatever it looks like, it's continuous. There are no breaks. But to be discrete means that it's not continuous, which means that we can't use every single number in the real number system as inputs, and therefore we're not going to get a continuous graph. We're going to get just a set of disconnected ordered pairs. And the reason why it's discrete is because with geometric sequences, we're interested in finding out a certain term in the list, like the first term or the fifth term or the 12th term. It doesn't make sense to look for the 11.5 term. Okay, all of the terms are basically, well, they're just going to be non-decimal, non-fraction inputs. Okay, so that leads us to a formula to help us find any term in a sequence. And so this is a new formula, and I want you to see how it compares. The whole reason for this slide is to see the connection between exponential growth and decay, which we've already talked about, and this new formula that is, we're going to use it a lot in today's lesson, helps us to find any particular term in the list, whether that's the first term or the 21st term. This will help us find it. There is no such thing as a 0th term. Okay, the terms start with the first one, and then they continue on for however long the particular sequence is. And we're dealing with finite sequences, so they do have a definite ending point. So maybe they start with the first term, or the sequence starts with the first one, and then it ends with the 19th one. So this formula helps us find any of those without having to actually do the multiplication and come up with the list. All right, so using this example over here on the left and using this formula that I've been provided, here's how it would work. So to find the first term, that means n is 1. So this little notation here means the first term. We'll use the letter A for terms, and then whatever term we're looking for, that will be n. So this represents the first term. Well, obviously the first term we already knew, because we can either take looking at A, or we can plug in 0 for x, whichever. But the initial value is another way of saying the first term is 3. And then this r, remember that stands for common ratio. Well, if you compare the exponential growth function to this, it looks like r is this base for the exponent, and so r is 2. And then for finding a particular nth term, the exponent is going to be n minus 1. And so in this particular case, n is 1 minus 1, which is going to give us 0. So our first term is 3 times 2 to the 0 power. 2 to the 0 is 1. 3 times 1 is 3. Okay, so the reason for this n minus 1 is, well, when we're dealing with terms, again, we always, well, when we're generating the entire list, we want to start with the first term. But this function, basically to draw the graph, we start with the y-intercept, which means x would have to be 0. And so we kind of walked through over here how to get the second term. We actually put in, well, let's go back to the first term. The first term meant x is 0. Second term meant x is 1. Third term means x is 2. Notice how it's 1 less, and that's why this formula has n minus 1 as the exponent. Okay, so to get the second term, we would call it a sub 2. The first term is still 3, and r is still 2, but notice how the exponent n became 2, that subscript. So 2 minus 1 is 1, and 3 times 2 is 6. So first term, see how they match? Second term, second term. All right, to find the third term in this list, we would have the first term times r to the n minus 1. N is 3 in this case. 3 minus 1 is 2. So 3 times 4 is 12. Third term, third value as our output. And then the fourth term, a sub 4, first term times r to the third. 2 to the third is 8. 8 times 3 is 24. Okay, so I just wanted you to make that connection. Really, what we're doing today is a discrete function form of what we've done previously. Over here, the input for x can technically be anything because the graph is going to be continuous. But in geometric sequences, we're looking for particular terms to make the list, and there's no such thing as a 3 1/3 term. Okay, terms are going to be basically natural numbers, okay, as inputs. All right, so with that said, I've already covered a lot of this, and so let's go over some homework examples. This will be the type of thing that you do on problems 18 through 21. So once again, just a reminder, a sub n in words would mean find the whatever term. If you're finding the 8th term, that would be a sub 8. And so here's another example. A sub 3 means to find the 3rd term. All right, so once again, you'll do yourself a favor if you get real familiar with this formula to help you find any nth term. So here's what that means. I can find any term I want, any nth term, by taking the first term and multiplying times r to the n minus 1 power. All right, so here's letter A. Apparently, according to this, I'm finding the 11th term. N is 11. So the first term is given as 18, and r is given as 1/3. And the exponent for 1/3 is going to be 10. It's going to be 1 less. So now you can grab your calculator. And so I've gone to my calculator, and they don't really tell you how to round these. And so for letter numbers like this, there's an answer in the book similar to this, and it's to 7 decimal places. So I would say at least 7 decimal places. So that should be what is showing on your calculator display, 000304832. And so that represents the 11th term in this particular geometric sequence. All right, so here's another one. According to this, I'm finding the 13th term. So a sub 13 is going to be found by taking the first term, which is 3/7, and multiplying by 4 raised to the 12th. It's always to the n minus 1 power. So 3/7 times 4 to the 12th. Looks like that's 7,1. Let's go ahead and put this 719,025.429. Okay, moving on to letter C. It's given a little different way. We're supposed to find the 8th term, and they give us the first term, but they don't just come right out and tell us what the common ratio is. So remember, you can always find it, probably pretty obvious that you're multiplying by 3. But if it's not obvious to you, just if you truly do know that it's a geometric sequence, then you can find R if it's not obvious just by pairing these up, like these first two, and always do the second within the pair divided by the one before it. And then 3/8 divided by 1/8 is the same thing as 3/8 times 8. And so 3 is the common ratio. Okay, so R is 3. So we'll find the 8th term, a sub 8, by taking the first term, which is 1/8, multiplying times R, which is 3, and then raise R to the 7th power. All right, so let's go to our calculator. And it looks like that's 273.375. All right, very good. Moving on to our next set of problems. In this set of problems, you're going to be writing an equation for the nth term. So they begin to describe a geometric sequence, and it's kind of working backwards. We're gonna write the equation that represents this sequence. And so remember, we're still dealing with this same formula. A sub n equals a sub 1 times r to the n minus 1. And we want to leave this open so that it could be used to find any nth term in this sequence. Okay, so don't try to get specific. We're going to leave it open. So it really amounts to this. If we're given the first term like we are here, then we know what a sub 1 is. The only thing we've got to come up with is what is r. And you can probably tell that r is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. So the equation for letter A will be a sub n. I can find any nth term by taking the first term, which is 2, multiply by r, which is also 2, and raise that to the n minus 1 power. So that is my answer for example A. Example B is a little different because they give you the second term, and you have to have the first term to use this formula. So again, you can always do division. If you divide negative 96 divided by negative 8, you get 12. And so the first term has to be 12. So another way of checking yourself is if you take the first term times negative 8, you should get the second term. All right. So my equation is going to be some nth term can be found by taking the first term, which is 12, multiplying by r, which is given as negative 8, and raising that to the n minus 1 power. All right, pretty easy so far. And then letter C, we're given the fourth term, so we're going to have to do this division a few times to get us back to the first term. So 54 divided by 3 would be the third term. 18 divided by 3 would be the second term. 6 divided by 3 would be the first term. So here we go. We can find any nth term of this sequence by taking the first term, which is 2, multiplying by r, which is 3, raised to the n minus 1 power. All right, very good. All right, let's do another type of problem where we're asked to find the geometric mean. And geometric mean, I'll show you how to determine that. That's used when we have a missing term in between two different terms of a geometric sequence. Okay, so notice how I've got 3, and then I've got some term, and then I go to 48. And if I'm told that this truly is geometric, then I have to be multiplying by the same number each time to get to the next term. So to find the missing term, you use this concept called geometric means. Really pretty easy. It's the square root of the product of the two outside numbers. So go to your calculator, and you're going to do the square root of 3 times 48. And you get 12, and that is that missing term. And you can check yourself. Geometric sequence should be multiplying by the same number every time. So looks like 4 is that common ratio, and that works. And so here is how you calculate, or how you find those missing terms. You use the geometric mean concept. Okay, sometimes there are 3 missing terms. So in cases like this, we're going to focus on finding the one in the middle first. So once again, that's going to be geometric mean. So just take the term on the extreme left, multiplied times the one on the right, and then do the square root of that. So go to our calculator, and that's 4. And now it's easy enough. Use that same approach to find the left missing term and the right missing term. So the left missing term, you will do the square root of 0.25 times 4, which should be 1. And the right side missing term, you'll use the square root of 4 times 64, geometric mean. And that's 16. And you can check yourself. Looks like the common ratio is going to be 4. And that holds true as I go from one term to the next. And so these are my answers. These are my 3 missing terms. And that's the kind of thing you'll be doing on 35 through 38. Okay, let's just go ahead and try this one. We're going to do, to get the middle term, we'll do the square root of 0.20 times 125, geometric mean. 0.2 times 125, and that's 5. 5 is the middle term. And now we'll do geometric mean for the left side. Square root of 0.2 times 5 is 1. So you can already tell that the common ratio is going to be 5. And 5 times 5 is 25. So really, you can probably get by with, most of the time, unless it's a fraction, it might be a little harder to see. Once you found the geometric mean of this left side, it probably, in some cases, will be obvious. And so you won't have to do geometric mean again. Okay, so sometimes we have problems like this. There's 2 of them in your assignment where you're asked to find 2 geometric means. So it's implied, obviously, that there are a total of 4 terms. The first one is 4. The last one is 1372. And we want to know what the 2 terms between are. So it's really like saying this. What are these 2 terms? So it makes it tough to just obviously write these in because we don't know what the common ratio is. So what we're going to do in this case is we're going to start with this formula, which is the formula we talked about early on to help us find any nth term of a sequence, geometric sequence. And since we know that there are 4 terms in this list, then n is 4. So a sub 4. We also know the first term is 4. We don't know r yet. We're going to solve for that. And then the exponent for r has to be 3. Okay, so this really amounts to solving for r, and then it'll be pretty obvious what these numbers are going to be. All right, so a sub 4, I can actually put a number here. That means the 4th term, and that's 1372. Okay, so to solve for r, I'm going to divide by 4 first. 1372 divided by 4. That's 343 equals r cubed. And now I do the cube root of both sides. So you can just raise that to the parentheses 1/3 power, and you get 7. So now it's going to be pretty easy to come up with these two missing terms. 4 times 7 is 28, and 28 times 7 is 196. Okay, so that's how you'll go about doing these two problems. And let's move on. Now we're leaving sequences, and we're going to talk about series. And remember, the only difference really is a series is the sum of the terms in a sequence. And so there's another formula that we're going to learn to help us find the sum of a geometric sequence. And it looks like this. The sum of a certain number of terms can be found by taking the first term, multiplying by 1 minus r to the n power over 1 minus r. Okay, so make yourself use that formula. It's going to be required that you know this, and make sure you're using your calculator correctly. It's not really hard to use, but sometimes it's hard to remember. So make sure you drill it as you have the opportunity in doing your homework. So in letter A, we're supposed to find the sum of 10 terms in a geometric sequence. So S sub 10, the first term is given, 2, 1 minus r, which is 3, and raised to the 10th. Notice it's not n minus 1, it's just whatever n is. And then that's divided by 1 minus r, and again, r is 3. So you can go to your calculator now and do all of this. 2 times 1 minus 3 to the 10th. And if you don't trust yourself to just say divide by -2, you should know this by now. If you divide by 1 minus 3, then the operation 1 minus 3 needs to go in parentheses. That's crucial. That will mess up your answer if you don't put 1 minus 3 in parentheses. So let's see what we get. 2 times 1 minus 3 raised to the 10th power divided by -2. And it looks like we got 59,048. So that is our answer for letter A. Okay, letter B is this. It's also showing the sum, but this is in what we call sigma notation. Okay, sigma is this Greek letter. It looks like an E shape. Uppercase sigma, which is what this is, always refers to the sum of when it's used in a math context. So sigma notation, sometimes also known as summation notation, is really a shortcut way of showing the sum of an entire series. So let me just run through this real quick and give you an idea of how this works. So in summation notation, to come up with the first term of the list of numbers that I'm supposed to add up, I take this number down below, it says k equals 1, and I input that number in for k. Well, this goes back to what we talked about previously. That's going to give us the initial value, or the first term, and you should see that the first term is going to be 3. Okay, so that's the first term. The second term to get the second term, I'm going to take 2 and put it in for k. So negative 2 squared is 4. 4 times 3 is 12. All right. To get the third term, you can probably tell how you're going to sorry, I just realized that I didn't do that very well. When I put 2 in for k, I do 2 minus 1. That wasn't very smart. So 2 minus 1 is 1, and negative 2 to the first is negative 2, and then negative 2 times 3 is negative 6. Sorry about that. All right, so to get the third term, I'm going to let k be 3. 3 minus 1 is 2. Negative 2 squared is 4. 4 times 3 is 12. So you can either keep doing this by letting k go up by 1, or you know what the common ratio is, negative 2, so you're going to be multiplying by negative 2 each time. So the next one should be negative 24. The fifth one should be 48. And then the sixth one, according to this, the upper limit is 6. So we stop at the sixth term. And if we multiply by negative 2, we get negative 96. So what this says is for it to be a series, we should add up all of these numbers. And when we do, if you were to add up all those numbers, you would get the sum. Well, we have a formula to help us get the sum. Remember, for the sum of any finite geometric series, we're going to do this. Okay, so according to this, we've got starting with the first term, ending with the sixth term, n is 6. First term is 3, 1 minus r, which is negative 2, to the sixth, all over 1 minus r. Okay, so let's go ahead and go to our calculator and key this in. 1 minus negative 2 raised to the sixth power. And we're going to be dividing by, I'm just going to say dividing by 3. Okay, so again, if you don't trust yourself to do that, if you want the calculator to do everything, make sure you put that whole denominator in parentheses. All right, so 3 times, you really have to be careful here, 1 minus, and then I'm going to put negative 2 in parentheses, raised to the sixth power. And then I'm going to divide that by 3. And I got negative 63 as my answer. So let's just check ourselves. Let's see what we get if we just, the old-fashioned way, we listed out all the terms. If we add them up, let's see, 3 plus negative 6 is negative 3. Negative 3 plus 12 is 9. 9 plus negative 24 is negative 15. Negative 15 plus 48 is 33. And then 33 plus negative 96 is negative 63. So especially when you're dealing with a lot of terms in a sequence, this formula comes in handy for you. Okay, so to wrap this up, there's a couple of word problems that I just want to set up for you, and then I'm going to let you finish. And there's other word problems that are closely related, very similar to these. So I just want to point out something. Number 17, we're in Brianstown, and because of rain, the Pecos River is rising. It rose 3 inches the first day, that's our initial value, and then each day after that it rose twice as much as the previous day. So the question that is to be answered is, how much did the river rise in 5 days? Notice, it did not say how much did the river rise on the 5th day. It wants to know across the 5 days, what is the total amount that the river rose? So we're looking for a sum of a geometric sequence, which is also known as a series. And so on this problem, you're going to use your sum formula. And let's just go ahead and set this up. We need the first term. So it rose 3 inches the first day. First term is 3. And it rose twice as much. Each day it rose twice as much as the previous day. So R is going to be 2. 1 minus 2. And we're doing this across 5 days. So N is 5. Okay, so I'll let you take it from there, but I just wanted to point out the difference of when you're using a sum formula, which is you'll just have to read the question, versus questions like this, which really represent exponential growth or decay. Whenever things, or it could be people if it's talking about population, but in this case, we have bacteria that's growing exponentially. Whether maybe it's a virus, it could be either a computer virus or just otherwise health virus that's spreading at a certain rate, then this is really just another way of saying exponential growth. So remember, exponential growth could be represented as this, or in cases of the discrete form of exponential growth, which we call a geometric sequence, we can just look for a particular term by doing this. All right, so since this is the formula that we're just gotten exposed to, we'll just go ahead and use it. So according to this, the bacteria is growing at a rate of 3 cells for every 2 minutes. Okay, so since it wants to know how many there are after 21 minutes, let's just think about this in terms of 1 minute. Okay, 3 cells every 2 minutes means that's 1.5 cells every minute. Okay, so let's see. We want to know basically what is the 21st term. So A sub 21 is going to be taking the first term, and we're told that there were 260 cells initially, so 260 is our first term. And our rate of growth, which is R, common ratio, is 1.5. And then the exponent will be to the 20th. All right, so I'll let you take it from there and see if you can come up with your final answer. But when you see other problems, let me just go and give you a heads up. You're going to do problem like number, on the wrong page, get back to the page. Number 51 will be like this one. Number 61 will be like this one. And then number 59 will correspond very closely to number 22. So maybe that'll help you out a little bit. Okay, so I just wanted to give you some help for that homework assignment, and I hope that does help you. And the assignment is there on your notes, or it's in RenWeb. So if you have any questions, let me know.